Welcome to lesson 18, in which we're going to be solving some polynomial and rational inequalities. We're going to extend the work that we've done in the past with graphing a little bit and then adding on another method along the way. Now, to start out with, one of our easier of the polynomials is just a little linear equation, and well, actually a linear inequality. And so I picked one that hopefully you remember from maybe an Algebra 1 class in high school. 2x minus 5 is less than 3. Now I know you can solve that very quickly and very easily, but I kind of want to build on it. So if you'll humor me, what I'd like to do is start out by graphing. And what I'd like to graph first is y equals 2x minus 5, that left-hand side of the inequality. Well, you know this is a straight line, and he has his vertical intercept at -5, and he has a slope of 2. So getting several points up through there, and I draw my line. Because what I want to do is let the picture illustrate for us what this means. We're looking for where 2x minus 5, which, by the way, on this graph is represented by our y coordinates, I want to know where that's less than 3. So what we can do is just kind of mark off, well, along this horizontal line, all of my values are equal to 3. So where are my y coordinates less than 3? Well, all along this line, this part of the line. Actually, it's a ray. So then the question would be, what is x so that this is true? Well, I mentioned in a previous lesson something I kind of stole from a colleague of mine, and that is you can think of kind of collapsing it down onto the x-axis, because what I want to do is find out what my x values are. So these will collapse down and these will all collapse up, and right here are those x values that I'm looking for. So it appears that my solution is going to be in interval notation from -infinity up to 4. And it's going to be open on the 4 because we can't equal 3, we have to stay less than 3. Now this particular guy is really easy for us to also solve algebraically. So, and I know you probably have already done that, 2x minus 5 is less than 3. Remember that you solve an inequality following exactly the same steps as solving an equation. You only have to be careful to change that inequality sign when you multiply or divide by a negative. Okay. Well, I'm going to add the 5, so the inequality stays put. 2x is less than 8. Divide by 2, x is less than 4. Which, in interval notation, is exactly what I have up there. So what we have here is both the algebraic process, which was very nice and easy, and we have a picture to illustrate the exact same thing. All right? Well, now we go up to the next simplest polynomial. We're looking at a second degree, or a quadratic. And essentially what we're going to want to graph is y equals this. Y equals x plus 3 and x minus 5. And we have graphed the polynomials in the past, and so you might remember when we talked about how in factored form this very quickly shows your zeros. So I know my graph is going to cross the x-axis at -3, because -3 is what will make this factor equal to 0. And I know it crosses my x-axis at 5, because +5 is what will make this factor equal to 0. Now, if you did multiply this out, I think you can easily see that we would have a positive 1x squared. So this parabola is opening upward. Now, I could find his vertex. It'd be pretty easy, really, but I don't need it, because all I need is a rough idea of what's going on this graph. Hey, I even put a little note over here. Boy, that 0 was nice, because I'm asking then, where is this product, which I called y, where is that greater than 0? Well, that's where are your y coordinates greater than 0? That's going to be anywhere above this x-axis. So where are those values for x? Well, it's going to be anywhere along this portion of the parabola, and you know that continues on forever, or anywhere along here. And technically we have open circles on our axis because we can't let it be equal to 0, strictly greater. And then if you do that idea of collapsing it down onto the x-axis so that you can see where your x values are. My x values are to the left of -3, and they would all be to the right of +5. So if I write my solution in nice interval notation, it would be -∞ up to -3, open, union 5, open, up to +∞. Okay, now, even though this is a quadratic, and you've done a lot of work on quadratics, let's think for just a moment about what it would take for us to deal with this algebraically. And the reason I'm doing this is I want to convince you that graphing might be a better option. Okay, here's what I mean. I have two quantities, a times b, and it's supposed to be greater than 0. Well, what kind of numbers are greater than 0? Those would be our positive numbers, right? Well, then the question is, under what condition can I multiply two numbers and get an answer that's positive? Well, there's actually two possibilities. You remember that from when you first learned working with signed numbers. If A is positive and simultaneously B is positive, then their product is positive. Or, and I am using proper logical connectives here, they're both negative. A is negative and simultaneously B is negative. Okay, so back in the old days when I was in algebra class, we actually would have to set up these two cases. And we'd have to consider, well, when is x plus 3 positive and x minus 5 is also positive? Then we had to consider the other case. When is x plus 3 negative and x minus 5 is also negative? Now, it's not that difficult, but you know what? This is way easier. And especially when you have already mastered the skills of graphing, it's a very nice way of looking at it. Okay? So let's go on and look at a cubic. We seem to be moving up by degrees. We do have a polynomial. He's a third degree. And I put a little note here. You know that 0 was really nice the last time because y is 0 right along that x-axis. That means that if I can find my x-intercepts, which you know we've practiced doing, then I'm going to have a very good start to getting this solution. Well, let me do the algebra over here because I'm going to have to do a little work to start. The first thing that I would do is bring these two terms over to the left-hand side because I really would like to have the 0 there. So that'll be a minus 4x and a minus 8, and it would be less than or equal to 0. Okay? And then you take a second and look at it and ponder. I have 4 terms. it is a third degree. It's a third degree, and I'd really like to factor it. The way we ordinarily can do these is by grouping. Grouping by pairs is the most common, and we get x squared times x plus 2. And factoring out of these two is a minus 4 times x plus 2. And now I've got two big terms here. So you look for the common factor, and the common factor is x plus 2. The remaining factor multipliers are x squared and minus 4. And I can factor that x squared minus 4. I get x plus 2 times x minus 2 times x plus 2. Nice little difference of squares, right? And then, because I've got two of these identical, it'd probably be a good idea to go ahead and write it this way. X minus 2 times x plus 2 squared, because you know that 2 makes me think of what word? Multiplicity. Less than or equal to 0. Okay, well let me write that over here and let's go ahead and graph x minus 2, x plus 2 squared is less than or equal to 0. Now you know from working with our polynomials before, I'm going to want to graph y equals this. He will cross the x-axis at 2. And we have a multiplicity of 1, which means he goes straight through the axis, right? Either he goes from below straight through to the above, or he goes from above straight through to below. At negative 2, and I'm getting the negative 2 from here, I have a multiplicity of 2, which means he bounces. Now there's one more thing that I need before I go ahead and draw this graph, and that is end behavior. Remember we talked about end behavior. Well, first off, what if I didn't have that? If I simply look here, I've got x to the first, I have an x squared. If I multiply that all out, I get an x squared. And an x squared times an x is a 1x cubed. That would be my leading term. And, in fact, you see it right there. That's my term with the highest degree. Remember, he determines what everybody else is doing as the numbers get really large. So for a cubic, his end behavior looks kind of like that. Okay, which means I'm going to start down below because he's coming from below. Now when I hit this negative 2, I have to bounce. So it comes up and it hits the axis and then drops. And then at positive 2, it has to go through the axis. Remember graphing those in a previous lesson? And the nice thing is that now I'm looking at a picture that should help me solve this inequality. Because the question is, when is all of this, which is my y coordinates, when is that less than or equal to 0? Well, you know, right along this x-axis is where it's equal to 0. Y is less than 0 below. So I'm effectively trying to figure out for what values of x is this curve on the x-axis or below it. Well, that happens to fall from here all the way through, and I touch the axis again, but that's okay. And then it drops. So it's all of this as far as x coordinates. So my solution set would be from negative infinity up to positive 2, and the endpoint is included, so I put a closed symbol on the end. Now just for fun, I said, oh, let's think again about what this would be if we had to solve this algebraically. We do have 3 factors. Now we are actually helped by the fact that this guy is squared. And if he's squared, that means he's never negative, right, in the real number system? Which essentially means that only this factor determines positive or negative. Only that factor. That's kind of interesting. But that takes a higher level of thinking, and we were helped by the fact that there was this squared term. Without that squared term, a cubic could be quite a headache to try to work with as far as what would make it positive or negative. So graphing is a very good option, especially since we've practiced graphing polynomials. Well, now I'm giving you a much bigger polynomial, but the nice thing is, first off, we've got them set to be greater than 0. Oh, how nice, because that means that I'm strictly looking for intercepts or roots. You know, they're the same thing. And it's nice that this is all in factored form. So I can just look at this to get my roots. The 2 is not adding to the roots. This factor is 0 if x is 1. This factor is 0 if x is 4. Although isn't that kind of odd? It's written backwards of what we usually see. We'll come back to that. This factor is 0 when x is negative 3. Now, in order to figure out how I wind through there, I need to think of 2 more things. I need to think about multiplicities. This factor at 1 has a multiplicity of 2. This factor at 4 has a multiplicity of 1. And this factor at negative 3 has a multiplicity of 3. Hey, if I add up all those multiplicities, degrees, what do I get? I get 6. So as far as end behavior is concerned, this is a 6th degree, meaning that if I multiplied all this out, which could just take you forever, you would end up with an x to the 6th. Now with an even power, it means that we either have this or we have this. Previous lesson. You might need to go back and refresh your memory on that if you've forgotten that. In order to determine which of these is happening, I have to determine if the leading coefficient is positive or negative. Now I threw a little oddity in here for you guys, because a lot of times we simply look right here and say, oh, that's a positive 2. But I wanted the chance to show you something a little different, okay? Most of the time this guy will tell you. However, I want you to look a little deeper. If this gets multiplied out, we would have an x squared as a leading, the highest degree term. Now this guy, there's no multiplying out to do, but notice that that's a minus x. So when I take this x squared times the minus x, oh, I get a negative. When this all gets multiplied out, the highest term would be x cubed. So if you actually multiply those all together, your highest degreed term would be negative 2x to the 6th. Now I know that was a little bit tough on you, but it was because this was coming behind the minus sign. We didn't really do that much in the previous lesson. Because that coefficient is negative, it means here is my end behavior. So I come from below, hit my first x-intercept. He has a multiplicity of 3, so I just S-curve through. Now at 1, we have a multiplicity of 2, which means I have to bounce it. And at 4, I have a multiplicity of 1. Boom. It's kind of an odd-looking graph, but that's my graph. It's not accurate, except it clearly indicates the zeros. Now for my solutions, I'm looking for where it is strictly greater than 0, not equal to 0, greater than. So that means I want to go to this axis, but I can't take the points that are sitting on there. I have to just go along here. And then you know what? It's kind of weird, but at 1, I can't take that. Because at 1, I get a 0 out of here. And 0 is not bigger than 0. And then I come over to there. All of that is greater than 0 on the y coordinates. But you know, to solve it, it means you need to know what are the x coordinates. Collapsing that onto the axis, I have this. Little bit of an odd looking thing, but my solution is from -3 up to 1. It's open circles on both ends, and 1 up to 4. Again, let's think about how that would work algebraically, trying to figure out with these 6 factors. Now we have some repeated factors here, but we've got 6 factors going on. How in the world are we going to get positive results out of these 6 factors? I think you can realize that by now you'd really want to call Uncle. You're way better off to go ahead and get a rough sketch. And that rough sketch is enough for me to know exactly what those solutions are. Okay? Well, we're no longer in polynomial land. We've changed. We have a rational now. And I picked a rational that wouldn't be too bad to get started with. Remember, we graphed these before. When you've got a fraction in which the numerator is a polynomial, the denominator is a polynomial, that gives you a rational expression or rational function. Remember what happens where this denominator is 0? That's a vertical asymptote. So the denominator is 0 when x is 2. And then, by the way, let me note that vertical asymptote is x equals 2. You remember how we got our horizontal asymptotes? What we did was we took the highest degree term out of the top and the bottom, because the highest degree is the only thing that matters when we're talking about really large numbers. And we say y equals x over x. Well, that simply reduces to 1. So that's my horizontal asymptote, y equals 1. Okay. Well, from here we've got a pretty good idea of what's going to happen, but it's a good idea to find 2 other points, y-intercept and x-intercept. It's not awake, okay? To get my y-intercept, I put 0 in for x. So 0 in for both of those, we get a -5/2. By the way, if it bothers you that I'm working with it with the 0 in there, we might want to just clarify for a moment what I'm actually graphing. I'm really graphing y equals x plus 5 over x minus 2. I'm graphing that equation is what I'm graphing. Okay? That's what we did in a previous lesson, and we know the horizontal asymptote, the vertical asymptote. I know my y-intercept is at 0, -2.5. And I'd like to know my x-intercept as well. Since this is an asymptote, I would bet money, and I'm really cheap, but I would bet money that we're going to go up and cross that x-axis over here on the negative side. It's kind of nice to have a sense of what should be happening here. Well, do you remember how we get an x-intercept? Well, in that case, we're going to put 0 in for y. 0 equals x plus 5 over x minus 2. We're effectively multiplying both sides by x minus 2, which on the left just stays at 0. And of course, that solves with x equals negative 5. So my x-intercept is negative 5, comma 0. And you know, that's pretty much what I had thought would happen, is somewhere over here on the negative side it was going to hit. And so now I can reasonably draw that. And remember, we talked about how this denominator, you look at the multiplicity of that factor. And since that has a multiplicity of 1, just like on the polynomials, we're going to cross over. And what that means in this case is I'm crossing over that horizontal asymptote, and there is, it's not perfect. If you want, plot some points. But it's good enough for what I need. Okay, so I have graphed y equals x plus 5 over x minus 2. And now I can try to answer the question. My eraser still doesn't want to work. I can answer the question, where is it greater than 0? Well, remember, we're talking about the y values, and y equals 0 along the x-axis. I need to be strictly above it. Well, where is my curve above the x-axis? Well, all through here, that entire branch is, and left of that negative 5, because at negative 5 it crossed over, and it's going to go up next to that asymptote. So collapsing it down, it's not greater than 0 at negative 5, but everywhere to the left it is. And you know I can't count this asymptote because it's not even in the function, but I can take everything to the right of it. And so that green is showing you the x values that will make that inequality true. And that will be negative infinity up to negative 5, union 2 up to infinity. Now, I'll grant you, who likes graphing rationals? They're not a whole lot of fun, although they actually can have some cool graphs. But they're also a whole lot of work. I understand that. So I'm actually going to give you an easier alternative here. We're going to streamline this a little bit because it is so much work. However, before we do that, I want you to think for just a moment about what if I tried to solve this algebraically. Because, you know, being a hardened veteran math teacher as I am, I've seen students try just about everything. And they often tell me, oh, I know an easier way. I don't need that baloney. I'll just multiply both sides by x minus 2. You know, you did it just a minute ago. And so they set this up to multiply both sides of this by x minus 2. You're causing a problem. You're causing a big problem. Remember back on the very first screen when we had the nice easy inequality, I said we solve them the same as equations except when we multiply or divide by a negative. You're choosing to multiply both sides by x minus 2 to clear out this fraction. But is x minus 2 a positive number or is it a negative number? Well, that depends. On what? Well, that depends on x. If x is bigger than 2, you're multiplying by a positive. If x is less than 2, you're multiplying by a negative. Now, if you want to do this algebraically, you set up case 1, you set up case 2, and you go at it, all right? But don't just randomly multiply both sides of an inequality by a variable. You are asking for trouble. I can't do that without first clarifying whether x is greater than 2 or not. You're asking for trouble because you don't know whether you should change that inequality sign or not. Okay? So as we think about solving it algebraically, I think you're going to realize it's even worse than graphing the whole rational. But I'm going to show you a streamlined way. With this very same function, you'll notice it's x plus 5 over x minus 2. You'll see that I've gone into one dimension. We're only going to look at this one-dimensionally now instead of 2. If we go back here, and sadly all my stuff is gone, but that's okay. What happened over there is the asymptote cut. Because you know, a lot of times our functions will change location drastically at an asymptote. So here's the first thing you do. Look at where your denominator would equal 0. My denominator would equal 0 at 2. Now I'm putting a big open circle at 2 because I want you to see my open circle, and because it can't equal 2. Okay. That is an important breaking point. And we saw that with our whole graph on the last screen. Okay. Well, then another place that would matter is where these are equal to 0. And you say, well, why does the equal matter? Because 0 is going to be your dividing line in a sense. Being equal to 0 is that dividing line between being above it and being below it. So we want to find that dividing line. We want to find out where does x plus 5 over x minus 2 equal 0. Now, by the way, we did actually do this just a few minutes ago for a different reason. What am I going to do? I'm going to multiply by x minus 2. Now, I know somebody's saying, what? You just told me not to do that. Wait a minute. Wait a minute. I've got an equal sign. It's totally legal on an equal sign as long as I am not multiplying by 0. And the only way I would be multiplying by 0 is if x were 2, but it can't be. Okay. So I end up with x plus 5 is equal to 0 and x is equal to negative 5. That means that negative 5 is another breaking point for me. Now at negative 5, this is going to equal 0, which means that I'm going to want an open circle there because I don't want it equal, I want it bigger. Hey, by the way, if you go back and look at your notes from the last screen, you'll notice that these were my two very important points. Now, the only thing left to do is to realize that my line, my number line, has gotten split into 3 sections by these 2 points of concern, okay? And all I need to do is pick a value in each of those 3 sections. Assuming I've done everything correctly, then I pick one and I determine if it makes this inequality true. If it does, everything in that interval works. If it doesn't, none of them does. It's an all or nothing. Well, you can pick anything you like in there if there's one that you think looks nicer for a reason. I'm going to test x equals negative 6. No particular reason on that. Negative 6 plus 5 over negative 6 minus 2. what is that? Negative 1 over negative 8. Those negatives will cancel, right? And I get positive 1/8. Is that bigger than 0? You bet. Which means I want this whole region. This is good. Okay? This was true. Now I go into the middle section. Well, I see the 0 sitting in there, and I like 0 as much as possible. So we're going to test x equals 0. So I have 0 plus 5 over 0 minus 2. Well, that's what, 5 over negative 2? That's like negative 2.5. Is that greater than 0? So I don't want anything in that interval. Whole interval's gone because I didn't like 0. Hey, if you want, you might play around with some other values within the interval in order to get a better feel for why just testing 1 is enough. Okay? Well, let's take something bigger than 2. No reason to go crazy. We'll test x equals 3. Hey, by the way, do you notice that I'm showing you very clearly what it is that I'm doing each of these times? And that's a good thing as you turn in homework assignments or as you take a test or something, that you clarify to the reader what it is that you are doing. I'm going to test where x is 3. Well, that's 3 plus 5 over 3 minus 2. That's 8 over 1. That's bigger than 0. So I also want everything bigger than 2. And so my solutions, it still isn't going to work. My solutions are from negative infinity up to negative 5, union 2 up to positive infinity. And that's the exact same solution we got in the previous screen. I think this is easier. Okay? We're going to try this on several more examples. Okay? 1 over x minus 3 is less than 1. You'll notice we don't have that 0 this time, so we can't necessarily think positive, negative. Okay, so the question is, first off, what would make the denominator equal to 0? 3 would. Well, we can't let it equal 3, so I'm putting an open circle there. It can't be 3. But the 3 is where an asymptote would happen on the graph, and so it would be a breaking point. Okay. Well, then I need to check to see where I have equality, because equality is the breaking line between less than and greater than. So I have 1 over x minus 3 equals 1. Let's multiply both sides by x minus 3. And very quickly we get x is 4. And you can test that back and see real quickly, yeah, x is 4. Now, can x actually equal 4? Well, if I put in the 4, I get a 1, and 1 is not less than 1, so I would again put an open circle on 4. Now, if you take a look at your intervals, I've got from 4 up, I've got from 3 down, and then I've got this really narrow interval right in there. And we've got to decide. Hey, I have some students that say, oh, well, they always alternate. No, they don't. They sometimes alternate. In fact, maybe more than half the time they alternate. But just as soon as you automatically assume that, I'm going to throw you one that doesn't. So don't jump on that. Okay, well, let's do some tests. What would you like to pick to the left of 3? I like 0. So test x equals 0. 1 over 0 minus 3. That's a negative 1/3, right? Is that less than 1? Yeah. So I want from 3 all the way down. This next one's a little annoying because you're like, what's between 3 and 4? Well, there's infinitely many numbers between 3 and 4, including pi. Pick whatever you like. Unfortunately, you're going to have to pick a non-integer. Let's take 3.5, just because that might make you feel a little bit more comfortable. 1 divided by 3.5 minus 3. That's what 1 divided by 0.5. Do you know what 1 divided by 0.5 is? It's 2. Is 2 less than 1? Ooh. So we do not want this section. We got one more section to test. Let's take the 5, okay, right there. So test x equals 5. So we have 1 over 5 minus 3. That is 1/2. Is that less than 1? Yeah. So we do want this entire interval. And so my solution, I can see on my number line, is negative infinity, that's over here on the left, up to 3, open interval, union open interval, 4 to infinity. Okay? And I think that's actually a lot better than graphing the entire function and then trying to figure out where it's below y equals 1. I think this is actually much, much, much easier. Okay. Well, let's try another guy. Wow. Trying to do this guy by graphing the whole thing would be a nightmare. Okay? I don't even want to go there. So here's what I'm going to do. I'm going to take the negative 3. I'm going to take the 2. Now I also have to check, because you check to see what would make your denominators equal to 0. Then I have to see what would make that an equality. 3 over x plus 3 equals 3 over x minus 2. Well, that's just like a big proportion. We can cross multiply if you like. You can also think of clearing fractions, your choice. We get 3x minus 6 equals 3x plus 9. I multiply that way to get the 3x minus 6, multiply that way to get the 3x plus 9. Do you realize that can't be true ever? If you don't see it right now, let me subtract the 3x's off, and you get negative 6 is equal to 9, which is called a contradiction because that's untrue, which means those two guys can never be equal. Okay, simply means I don't have another point there to break things up. So I again just have 3 intervals. By the way, it isn't always 3, but I've got this interval, this one, and this one. Let's test some points. On the left here, let's take negative 4. And I have 3 over negative 4 plus 3. Is that less than? I'm putting a little question mark on there because I don't want to claim it is. Less than 3 over negative 4 minus 2. Well, that would be 3 over negative 1. Is that less than 3 over negative 6? Is negative 3 less than negative 1/2? Okay, so I have all of those guys. Wow, that took a lot of space for testing. How about if I do another test over here? Let's test 0. So I have 3 over 0 plus 3 is 3. Is that less than 3 over 0 minus 2 is negative 2. Well, no, I can't have a positive be less than a negative. So that's a pretty quick and easy guy. No. Seems like I'm always getting these outside parts. Let's try something bigger than 2. Let's test x equals 3. I have 3 over 6. I did the 3 plus 3. Is that less than 3 over 3 minus 2? 1. Is a half less than 3? Yeah. And so from 2 up, we're good. And so my solution is negative infinity up to negative 3, union 2 up to positive infinity. Okay? And again, don't assume that you're always going to get these outsides or whatever. And I do think this particular method of looking at this is way easier than anything else you can do. And thinking about doing this algebraically would just make me so unhappy. So let's recap. To solve an inequality, well, unfortunately, I don't recommend that you do them all the same way. So I said, all right, if you have a linear inequality, you know, linear is when you have a first degree equation or inequality. I said, solve it just like it was a regular equation. Just remembering to switch that inequality sign when you multiply or divide by a negative. Now, for any of your polynomials, and I clarified it with a degree bigger than 1, I would suggest that you get a 0 on one side and then you graph it. Get it all factored if it's not factored, and then assess your inequality by what's above the x-axis or below the x-axis. Okay? Probably your best bet with the polynomials, and especially the kind that we have a tendency to give you in a college algebra class. And then the third one is the rationals. And I don't think they're any harder, it just looks like my directions are longer. I said just work on a number line, not the whole graph. On that number line, first mark off anything that's going to make your denominator equal to 0, because that's where those asymptotes would be hitting, and you know that the curve often jumps around at asymptotes. Then change the inequality sign to an equation and solve that. Okay, mark those. Then do test values in those intervals. Okay, and that'll tell you where your answers are for that inequality. Practice, practice, practice on these. I don't think they're going to be hard, and hopefully you can kind of enjoy doing them. I'll see you in the next lesson.